Alright, welcome back everybody. So we are in section 5.3 talking about the definite integral as area. So we looked in section 5.2 just introducing the concept and notation of the integral, kind of what it gives us. Here we're really going to be looking at it as an area. So when we're talking about the definite integral, we have the integral from a to b of f of x dx. We say that that is equal to, just type this in over here, this is the area under the graph of f between a and b. Alright. So this is what the integral is going to give us, assuming that we have a positive function, and then a being less than b. So the area under the graph of f between a and b is going to give us the integral. So what we've done so far is, if we have our function, looks kind of like this, going from a to b. What we've been doing so far is we've been taking our rectangular approximations, rectangular approximations. So we've been drawing our rectangles here. Okay, and then that is giving us an approximation to the area under the curve. But what we want to be able to do is look at the area under the curve in its entirety from a to b. So that's this entire space down here. So this is going to be the integral from a to b of f of x dx. Alright, and like I keep saying, we will develop ways of calculating this directly, but that's going to come in the next chapter. For right now, we're just looking at it as an area, and looking at approximating areas, and just kind of interpreting what this could mean in different contexts. So, alright. Now, this is only if the graph is above the x-axis, right? If it's positive. If the graph of f lies below the x-axis, then the area between f and the x-axis is negative. Okay, now this is a general convention when we talk about integration and we talk about area under a curve, because of course geometrically area cannot be negative, right? It takes up space, but from a graphical standpoint with integration, if we have a curve that's above the x-axis, the area below it is positive, and if we have a curve below the x-axis, the area between the curve and the x-axis is counted as negative because it's below that x-axis. Okay? So let's look at this example here. So compare these integrals. So we have the same integrand here. We have x squared minus 1. So let me go ahead and just get a rough sketch of the graph going here. Okay, go 1, 2, 1, 2, 3, 4, down 1, 2, okay. So plot a couple points here. So the point 0, negative 1, the point 1, 0, and negative 1, 0, the point 2, 3, negative 2, 3. Okay, so this is going to be, this is going to be roughly what our curve looks like. Okay, and now for the integrals, what this is asking us for, so part A, the integral from 1 to 2 of x squared minus 1 dx. So this one is asking for, so there's negative 2, negative 1, 1, 2. This one is asking us for the area beneath the curve. So beneath x squared minus 1, but above the x-axis. Oops. Okay. But above the x-axis. Alright, and this is going from 1 to 2, so it's going from right here to right here. So this is the area in question for part A. So this is below the curve, but above the x-axis, so it is counted positively. And this, we could get an approximation for it. I'll just tell you what it is. This actual area is 4/3, okay, or 1 1/3. And we can get that using technology at this point, but we will see how to do that later on. Okay, and then for part B, we have the same integrand, but the bounds are different. So the integral from -1 to 1 of x squared minus 1 dx. So from -1 to 1, if you see where the curve is over here, this is the area that we're looking at for part B. So this is going to be the area above x squared minus 1, but below the x-axis. Okay, and this area, again, we can compute it using technology for now. That would give us 4/3, but because it's below the x-axis, it would give us -4/3. So it turns out that the amount of space taken up by both of these regions is the same. However, because one is above the x-axis, it's counted positively, and the one below the x-axis is counted negatively. Okay. Now, what if we have, like in this case, a combination, right? Because not every function is just above the x-axis or just below the x-axis. So when f is positive for some x values and negative for others, and a is less than b, then the value of the integral is the sum of the areas between a and b, with areas above the x-axis counted positively, and areas below the x-axis counted negatively. Okay. So, for example, if we were going to go back to this one, we saw that the area from -1 to 1 is -4/3. The area from 1 to 2 is +4/3. So the total combined area from -1 to 2 would be -4/3 plus 4/3, which is 0. So basically it has a net area of 0 because it's got an equal positive and negative component. Okay. So let's look at another example. So interpret the integral from 0 to 4 of x cubed minus 7x squared plus 11x dx in terms of areas. So if we were to graph this, just give you a rough sketch here of what this would look like. So we have there's 0, that's our origin. And we're going up to 4 here. Not quite. It's going to look something kind of like that. Roughly. Okay. So right now we can see that this has two clearly distinct areas, right? It has the area, the positive area up here and the negative area down here. So I'm going to call these, I'm going to label them separately. So I'm going to call this one A1 and this one A2. Okay. So in order to figure out where these areas get separated, we would have to find where this point is here on the graph. Okay, and that would be the point where the function is equal to 0, right? It's a root. So we would just go ahead and do that. So the graph crosses the x-axis at x is approximately 2.38. So this value here is about 2.38. And these, again, for right now, these are all just approximations. So if we were going to split up our two areas, A1 is going to be the integral from 0 up to 2.38 of the function x dx, which then we would get is approximately 7.72. And then A2 is the area from 2.38 all the way up to 4. So 2.38 to 4 of x cubed minus 7x squared plus 11x dx. So we've got our integrand there. And this value is approximately negative 5.05. So the value of the whole integral, so the integral from 0 to 4 of our function, is just going to be the sum of these areas. So A1 plus A2, which is 7.72, minus 5.05, which works out to be about 2.67. Okay. And if you were to go in and actually run this computation just using technology, you would see that it does give you approximately 2.67, but here, of course, we're looking at it as the sum of the different pieces, right? The positive piece and the negative piece. Okay. Now, when we're talking about area under a curve, right, or area between a curve and the x-axis, we can actually generalize this a little bit more. We don't have to just talk about curves above or below the x-axis. We can talk about areas between different curves. So we have, if f and g are continuous functions, so there's no gaps, no breaks in the function, and g and f, g is less than f for this interval, then the area between the graphs of f and g, for x being between a and b, is equal, I'm going to turn my pen on here, is equal to the integral from a to b of f of x minus g of x dx. Okay, so if we have that f is bigger than g on the interval, then the area between the two is just the integral of f minus g. So, for example, if we have our curves here, let me get a rough sketch of some curves. Something like this. Here's A. Oops. Here's B. Okay. What we would be doing with our rectangular approximations, this time instead of it just going from the x-axis up to f, now it's going between f and g. So we would draw a rectangle whose height is determined by both functions. Okay. And we would just keep, obviously, doing this all the way down the line until we reached the end. So that would give us our rectangular approximation, but of course using the value of the integral and just interpreting it as exact area, we would have, right, from A to B is just this whole area in here. Right, so if f is on top and this is g, so this area in the middle, that's going to be determined by f minus g, right? Because the area beneath f is going to be everything here. Right? That's all the area below F, but then the area beneath G is this part down here. So I want the area beneath F and then take out this portion beneath G, right? F minus G, and that leaves you with this portion up here, which is what, of course, we're talking about, the area between F and G. Right? So let's look at this example here. So estimate the area between the graphs of 4x minus x squared and 1/2 x to the 3/2. Okay? So if we look at the graphs of these, let me give a rough sketch here. Okay, so this one, so I'm going to do 4 on each axis. 1, 2, 3, 4. 1, 2, 3, 4. Okay, starting, oops, and our origin down here. Okay. So the first function, f of x, that's parabolic. You can plug in a couple points, right? 0, 0, the point 1, 3, the point 2, 4, okay, and then the point 3, 3, the point 4, 0. So this function's going to look something like this. And then the other function, right, we got 0, 0 on it. We've got 1 comma 1/2, and then if we jump up a little bit, we go up to 4, 4. So this one's going to look something like this. Okay, so this is F, this is G. And we want the area between these two curves. So that would be this area in here. Okay, that's the area kind of bounded by these two graphs. So in order to set up the integral, we would need to first know the bounds, right, from here to here. The first one we know, that's 0. They both intersect there. The other intersection point down here, we would find that via computation, set them equal to each other. This value is approximately 3.12. So the bounds, occur at intersection points. So, and again, that's x equals 0 and x approximately equal to 3.12. So if we were going to run this computation, so our area is the integral from 0 to 3.12 of top function minus bottom function, so 4x minus x squared minus 1/2 x to the 3/2 dx, which we could find then via technology to be approximately 5.906. 5.906 is our approximate value for that one. Okay. So we can find area beneath a curve, right, using the